Hello everyone. Today we are going to talk about measurement of process variables in the context of chemical process control. Now, we are well aware that any chemical plant consists of several processing units, and the overall objective is to convert the raw materials into useful products by consuming the energy in most economical manner. Now, to do this, while the process operates, we have some variables at hand like flow rate, temperature, pressure, which we need to monitor, which basically guides the process in the way we want them to go ahead. Now, during any chemical operation, the main concerns that we have are safety of the users or the operators, meeting the product specifications. I am writing in short form product specs, then complying with any process constraints. Suppose you are operating a reactor and you need to maintain the temperature between a certain lower and upper bound, then we need to comply with the process constraints or operational constraints. Then we also need to obey any environmental norms in case you are letting out some byproduct into a nearby river body. So all of these things have certain norms from the country's laws, environmental laws, where you can only discharge a certain amount of the chemicals into any natural water body. Also, we need to confirm or stand up to the current market conditions. So, depending on the demand, you will produce, and accordingly, you will plan the overall throughput through a particular process. So, to understand how these process variables are important, let us take the example of a CSTR. So, CSTR is a continuous stirred tank reactor. If you have studied a little bit about chemical reaction engineering, you would know that we have this continuous stirred tank reactor as one of the primary lessons in chemical engineering. So, what we have here is a liquid which is being reacted in a stirred tank reactor. This is the stirrer, and there is an input flow rate Fi, and the input temperature is Ti. These are process variables. The output flow rate is F, and the temperature is T. Also, for the reaction to occur, some amount of heat is being provided to the process with the help of maintaining a steam flow rate. So we have a valve here which will allow the steam to flow through this particular line. Now our process objective in this case is, say we want to maintain the output temperature at Ts. We want to maintain this T at Ts or a desired value, and also the entire volume of liquid in the stirred tank should be maintained at Vs. Now let us understand what are the probable things that can take our process away from these important objectives. So that outlet temperature can be affected by the input temperature, the input flow rate, also the steam flow rate. If there is any change in one of these three variables, then it can potentially disturb the output temperature T. Also, if there is some effect on this input flow rate, it can affect the total volume of the liquid in the stirred tank. So the major process variables PV that we need to be concerned about are FI, TI, and FST. So some action is required so that we can maintain these conditions in case these process variables are facing some disturbance. Now, this sets the background that we first need to identify our process objective, then identify the most important variables, and then understand what is required to be measured, and finally measuring them suitably. Now, let us talk a little bit about this process variables in brief. We'll take this CSTR example throughout this video. So, broadly, if we want to classify process variables, we can classify them as input variables and as output variables. So from this CSTR process, you can obviously understand that this FI, TI, FST, these fall under the category of input variables, whereas the output variables are F, T, and V. So V is an outcome of how the input variables behave and maintain the liquid level. So V is an output variable. Now again, these input variables can be further classified as manipulated variables and disturbances. So what are these manipulated variables? Let us go back to this process again. Suppose this stream is coming from some other upstream process which runs in your factory itself. So you can handle or adjust this temperature and flow rates as suitable in case you want to maintain this output criteria, that is T should be equals to Tns and V should be equals to Vs. But suppose if this stream was coming from some process which we do not know at all, which is from maybe some neighboring factory, then we would not be able to adjust this according to our need. Then we would have to do something in our process itself. So when we have a direct handle on the process variables, input process variables, we would call them manipulated variables. And if we do not have any handle on them, then we will call them disturbances. Now, in the same manner, the output can be classified into two categories. One is the measured output, and the other one is called the unmeasured output. Now, if the inlet stream of the CSTR, like I said, was coming from some other upstream process, then we would treat them as disturbances. Now, the effect of these disturbances on output needs to be measured. This is our main criteria, and that is how we classify whether an output can be measured or not measurable. So, N- right now the process that we have at hand, that is the CSTR process, whose output flow rate needs to be checked, the temperature needs to be checked, and the volume needs to be checked. All of these are measurable quantities. That is, if the flow rate can be measured using, say, a venturimeter, you can use a venturimeter to measure it. You have read it in your fluid mechanics lessons. If you want to measure the temperature, which we do need to measure in this case, then you can use a thermocouple. If you want to measure the volume, then you can use a differential pressure cell to measure the volume in the tank. Now, whether or not these quantities are directly measurable, uh, we can classify the disturbance as well into measured and unmeasured quantities. So I'll continue on this flow diagram itself. So disturbances can also be classified as further measured or unmeasured disturbances. So for example, this Ti and Fi over here, if they are the potential disturbances, then we can measure them directly using venturimeter and thermocouple. But suppose you have a distillation column. In a distillation column, what happens? Say you want to maintain the feed composition at the top, and like the top product feed composition needs to be maintained. I'll write it down. Feed composition should be maintained at a certain level. But this feed composition output cannot be measured directly, or if it is affecting some downstream process, then that cannot be measured directly. So then it will fall under the category of unmeasured process variable. If this top feed composition is disturbing some process further down the line, then we will call them unmeasured disturbances. And if this is the final outcome of the process and we need to maintain it at a certain level, then we would call this as an unmeasured output. So basically, no matter what our control objectives is, we need means to monitor the performance, and that can be done only by measuring the process variable of interest. Now the next thing we should think about is what to measure and what not to measure. So that is a big question for us. So our first concern is that if the control objective is directly related to any measurable process variable, I am writing PV for process variable, then we will make the measurement. This kind of measurement is called primary measurement. For example, like in the CSTR case, we wanted to keep T at T equals to Ts, so we can directly measure T. That is a primary measurement. But if the control objectives are related to some unmeasured outputs or outputs that can't be measured, what do we do in that case? So there is a simple solution for this problem. In that case, we will express the unmeasured output as a function of some secondary measurements. I'll give you an example of such a scenario. So, the unmeasured output can be expressed as a function of some secondary measurement. Now, let us take this example of distillation column again. So in a distillation column, we wanted to maintain the composition of top product or the distillate stream. Now to do so, what we can do is we directly use a composition analyzer. Okay, let me draw the distillation column for you. So this is a distillation column. This is your top product. This is your bottom product, and this is the feed. So FDB, bottom, distillate, and feed. Now your target is to maintain this particular composition at the top. So since this is directly related to our control objective, if we treat it as a primary measurement, what we'll do is we will use some composition analyzer. Now there are many composition analyzers available in industries, like you can have spectrometers, you can have potentiometers to measure the composition. So we will set a composition analyzer to directly measure this variable. But the performance of this composition analyzer is very slow, and sometimes it is also inaccurate. So what to do in such a case? In some cases, as a matter of fact, composition analyzers are very expensive also, and you may need to measure the composition at certain points throughout the column. So what do we do in that case? In that case, the best advice is to measure the temperature of the various trays in the column. So the trays in the column will all be evaluated for their temperatures using thermocouples. And these, so I'll write this down. Temperature of trays are measured using thermocouple. Now, if you have studied in your mass transfer course about distillation column, so you can relate the temperature of the trays with the necessary material and energy balances and thermodynamic equations, and then you can obtain the composition for the distillate stream. So we will make use of other process information as well to relate the unmeasured output with a known secondary measurement. I'll write down how we will do that, just in short, so that you can note it down later. So as you can see, here we have expressed d as a function of t. This is what we have essentially done. Now another thing that will actually be very helpful in case we can do it. So still now what we discussed is when we can make a direct measurement or primary measurement, and when we are expressing the unmeasured output as a function of some secondary measurement. But suppose we are able to measure the disturbances, say that temperature variable from an incoming stream is the major disturbance. So we can measure that using a thermocouple. In that case, what happens is we will record that measurement and we can take some remedial action. So direct measurement of external disturbance can actually lead to some remedy, that you can be prepared how to deal with the disturbance. So I'll write this down, that it leads to some remedial control action. So once the decision on measurements of process variable has been made, then we can start talking about the control logic. You may refer to some standard process control books. I will add the reference in the description box for your further study. These are some of the most basic examples, like that of composition analyzers being not so frequently used for measuring composition in distillation columns. Instead, we would like to relate the thermodynamic information obtained from temperature of trace, and then trying to measure the disturbance directly, use of primary measurement, and how we are classifying the input and output variables in as a as an overall picture. So after this, once you have decided what you want to measure and what are the most concerning process variables, we can go ahead and take up the further steps in the control action designing or control logic designing. Before we end this video, I'll give you a short thing to stay motivated, why we need to study chemical process control at all. Let me call this a chemical process control algorithm. So the first step is we will define the control objective. This is our first concern. The next step is we will select the necessary measurements. So right now we are in this step. We are trying to understand which variables are of interest to us and how we can measure them, or if they cannot be directly measured, how we can relate them to other measurable quantities. The next step is select manipulated variables. By this step, what I mean to say really is that how we affect the change in the process. That is, if some disturbance has indeed occurred, then how can we manipulate the process so that it is able to counter the disturbance? That is the selection of manipulated variables. The next thing is select the control configuration. By control configuration, what I mean is simply understanding the information structure that connects the available measurements with the available manipulated variables. And then the last step is to actually design the controller. This is basically the heart of your entire control, uh, how should I call it, like control loop or control action, is the designing of the controller. This is the most intelligent entity in this algorithm. So this is the last step. So we'll meet again in the next video, and we'll talk further about the measurements and how to link the right manipulated variables with the right measurements. Thank you.